watch afterwards.
I've definitely taken advantage of watching it afterwards, but not live. So that's interesting.
Very good. Okay, good. So YouTube, so it works. Okay, are you ready to start?
Yeah.
Okay, so I'm very glad to introduce Spencer Leslie from Duke University, who will speak about relative endoscopy for certain symmetric spaces.
Thank you very much for the invitation, Dima, and thank you all for coming. I've not actually been able to visit Weissman, though I've been trying for a couple of years, and it was actually, I was hoping to get there this last March, but unfortunately it was canceled due to COVID. So hopefully I'll be able to visit in person soon, but right now I'm very excited to be speaking in this seminar. So as Dima said, the title of my talk involves relative endoscopy for certain symmetric spaces. And so I guess the theme is the combination between the words relative and endoscopy. So the relative here is referring to the fact that we're interested in problems that are related to periods of automorphic forms or their relative trace formulas. And I'm going to be talking about a case of period integrals where there's motivation for trying to develop analogs of the tools of the theory of endoscopy in this relative setting. So a brief outline of my talk is I'm first going to review the relevant notions from the theory of elliptic endoscopy and the stabilization of the Arthur-Selberg trace formula, just to sort of recap kind of the main players that we're going to have relative analogs of towards the latter half of the talk. I'll then introduce the period integrals that are at play here. These are what I've called Unitary Friedberg-Jacquet periods. And I'll give a bit of like global and geometric motivation for studying these particular periods and sort of a putative comparison of trace formulas to try and analyze them. And that comparison will sort of clarify why we need some notion of stabilization to study this relative trace formula. And so at that point, I'll talk about my construction of endoscopic symmetric spaces for these particular periods and state the fundamental lemma, which is sort of the main result of this talk. And so my hope is for the last 20 minutes or so to sort of give a bit of the outline of the proof of this fundamental lemma, because there are some components of that proof which should generalize to other cases as well. And I'd just like to touch on that. And obviously feel free to ask me questions at any point. So let's start off with the review of endoscopy. So we're working on over a global field, and I'll say H is my reductive group. So we're interested in studying the space of cuspidal automorphic representations, or this L2 space. And so the main sort of spectral objects that we're maybe interested in computing are these multiplicities.
Excuse me.
Yes.
Can you come a bit closer to the microphone? I can't hear.
Oh, is that a, all right, one second. I'm using headphones. Is that better?
Yeah, now it's better. Yeah. Thank you.
No problem. Okay, so sort of a first principles, we're interested in computing these so-called automorphic multiplicities. And the tool, or one of the tools for studying this problem and computing these multiplicities is this Arthur-Selberg trace formula. So here, F is some test function on my group, and it acts via convolution on this L2 space. And so I just take the trace, and sort of tautologically, I have the left-hand side here, and the point of the trace formula is that this trace can also be computed in another way. So for the purpose of my talk, I'm just going to be focusing on the so-called elliptic part of the trace formula. There's many other terms that need to be handled, and that's a very interesting story, but we're not going to be talking about that today. And so the point here is that the elliptic part of the trace formula is a sum by conjugacy classes of elliptic elements over the global field of F. where each term here is sort of a standard orbital integral. And so Langlands' original idea, which leads to the theory of endoscopy, is that we can use this trace formula to compute these multiplicities by relating the geometric side to trace formulas on some simpler groups. Primarily in the case where H is a classical group, this will be GLN, and this is the like huge program of the stabilization of the twisted trace formula, culminating in Arthur's classification, endoscopic classification for classical groups. So this has been immensely successful. But the key problem here is that in order to do this, we need to stabilize this elliptic part. So just to sort of recall the things that are going to come up in a relative context later, I'll just sort of say the point here, the need for this stabilization is that when we want to compare these orbits to the other trace formulas, here we have a sum over conjugacy classes, but what we are able to compare are so-called stable conjugacy classes. And so I'll sort of just use the naive notion here, saying that gamma and gamma prime are stably conjugate if they're conjugate over the algebraic closure. So for some H over the algebraic closure. And so the problem here is that we need to have a geometric side indexed by these trace formulas. And so there's sort of two stages for this that are going to be parallel in the relative setting. So the first thing to do is to rewrite this as a sum over stable orbits. And also there's the problematic situation that you have these coefficients here, which are of a global nature. And so those were solved, this problem was solved first by work of Langlands and mostly due to Kottwitz, the so-called pre-stabilization of the elliptic part of the trace formula. And the point, the takeaway here is that we've written the elliptic part of the trace formula now as a sum over the terms that we want, stable conjugacy classes of elliptic orbits. And now it's a sort of a double sum, where inside we have this sum over these characters. So kappa here is just ranging over certain characters of a cohomology group. And our orbital integrals are now replaced by the so-called kappa orbital integrals. But you can see that this precisely solves the two problems I mentioned, namely that we're now indexing over stable classes rather than rational classes, and the orbital integrals are purely of a local form. So we can hope to study these things via local harmonic analysis. And in particular, if we take kappa equal to 1, we have the so-called stable orbital integrals, and that's what we want to compare. And so we have something of the form gamma is a sum of stable orbital integrals plus these non-trivial terms that we need to understand. And so the second task of stabilization is to really interpret these terms, these additional terms that come in this pre-stabilization. And this is what led Langlands to introduce the so-called notion of an endoscopic group. So that just again, as a quick rundown, the point is for each of these pairs, in the sum on the previous slide, I have a gamma, a stable class, and a character kappa. We should be able to define what we're calling elliptic endoscopic groups. I'll call HC associated to this pair, and there'll be some groups, reductive groups of smaller dimension. And these should come equipped with an inclusion of stable conjugacy classes from the endoscopic group to the group H. This allows us to compare the terms that arise in the trace formula. So to make that more precise, we have this notion of transfer. So if we have a test function on the endoscopic group and a test function on the group H, then we want to be able to compare the stable orbital integrals on the endoscopic side with these kappa orbital integrals arising on the in the trace formula of the group H. And so here, I want to point out that the critical construction in this case is the so-called transfer factor. So this is the Langlands-Shelstad-Kottwitz transfer factor. And once we have, I mean, these are very intricate objects, but once we have them constructed, we have a notion of what it means to match orbital integrals for matching orbits, matching in the sense of this comparison. And so this is very like rough. There's a lot of details I'm omitting, but the most important comparison, the most of test functions is the so-called fundamental lemma, which was proved by Ngo following work of Walsh-Bourget and Hales, reducing it to a Lie algebra situation. And the point there is that we're going to have in the unramified setting, so now I'm thinking a local p-adic place, I'm considering an explicit matching of test functions, where here I have the indicator function of some hyperspecial subgroup on H and a hyperspecial subgroup on the endoscopic group. So the point of this slide is just to kind of remind us the broad strokes of what goes into stabilizing the elliptic part of the trace formula. And so the first thing is to actually give a definition for these endoscopic groups. And it should be in such a way that we have this matching of stable classes. And two, we need to develop a good notion of a transfer factor so that we can actually meaningfully compare orbital integrals, stable orbital integrals on the one hand and kappa orbital integrals on the other. And the third thing is to prove the fundamental lemma. So there's more steps. I'm obviously not talking about the proof of smooth transfer or other results, but these are sort of the three main things that are going to come up later in the relative setting. So that's all I want to say about recapping endoscopy. And for those of you who may not recall the construction of endoscopic groups, I'm going to come back to that later. With that, I'm going to move on to the relative part of the title. So this is, as I mentioned previously, we're interested in not just automorphic forms on one group, but pairs of groups. So here I'll have a larger group G, and I'll take a closed subgroup H of G. And the problem that we're interested in is taking automorphic representations, say pi, on the larger group, and asking if the so-called period integrals, these are sort of regularized integrations of automorphic forms over this closed subgroup, whether or not these period integrals are non-vanishing. And so when we have such a non-vanishing statement, we call these automorphic representations distinguished by H. And so this is sort of the primordial problem in the relative Langlands context, is to study H distinguished representations. And so the goal here is to stabilize the elliptic part of a relative trace formula associated to a certain pair, G and H. And so what pair are we interested in? These are the so-called unitary Friedberg-Jacquet periods. Okay, so here I'm now working with unitary groups, so I have a quadratic extension E over F. And I'm going to take two n-dimensional Hermitian spaces, so they're the same dimension. And associated to these, I get the two unitary groups. And I can form the following inclusion of subgroups. So if I take the direct sum of my Hermitian spaces, I have a larger unitary group, and I get the inclusion of these two smaller unitary groups commuting inside. And so I'm interested in studying automorphic forms on G of A, which are distinguished with respect to this subgroup. So why do I call these unitary Friedberg-Jacquet periods? Well, the point is that these are sort of a unitary version of what Saul Friedberg and Herb Jacquet studied in the mid-90s, where if we just forget the Hermitian structure and think about the underlying linear groups, we have this inclusion here. And they studied these periods in the mid-90s and referred to them as linear periods. And some people, I think, are okay calling the case that I'm interested in unitary linear periods, but I just find the phrasing unitary linear somewhat problematic. So I opted instead for the attribution to Friedberg and Jacquet. So it'll be somewhat relevant later for me to just point out what they actually proved in this case. So they have the following very nice classification of distinguished representations in this case. So I actually suppose I want to put here cuspidal. So pi is a cuspidal automorphic representation, and it will be distinguished by this linear period if and only if we have two criteria. One, we have a non-vanishing of the central L value, and also the exterior square L function has a pole at s equals 1. So what we would like is to prove an analogous result of this form for these unitary Friedberg-Jacquet periods. And as I mentioned, there's some sort of geometric reason that we would be interested in studying this case. Just to quickly sort of summarize what's going on here, the point is, since we're dealing with unitary groups, we can hope to relate these periods to special cycles on certain Shimura varieties. And that's exactly what happens here. So if we're careful about how we choose our Hermitian spaces W1 and W2, the inclusion from the previous slide can be kind of souped up to an inclusion of similitude groups. And as long as we've been careful enough, we get an inclusion of Shimura varieties, sort of the product of Shimura varieties inside the Shimura variety for the larger unitary group. So this, by the way, like in the simplest case, when n is equal to 1, this is just a Heegner point, but obviously generalizes for n greater than 1. And so the point is, if we sort of using the standard relationship between special cycles and periods, cohomology of Shimura varieties and period integrals, results on distinction for these unitary Friedberg-Jacquet periods can be related to the Tate conjecture for these Shimura varieties. And actually, you know, for people who are more arithmetic than I guess I am, there's more to be said here. Recently, just this year, Graham and Shaw, so this is in 2020, they considered this inclusion for specific choices, and they obtained some partial results towards the Bloch-Kato conjectures. In this case, in this context. And so extending their results in the other direction, again, requires some more information about these periods. And so how do we hope to achieve such a similar characterization to what happened with the case of linear periods? The approach is to consider the relative trace formula. So this is sort of the only slide where I'm actually going to have a trace formula, sort of a relative trace formula mentioned. Usually I'll just refer to them in terms of like comparison of orbits. But the idea here is similar to before. I have my test function, and instead of just taking the trace, I'm going to integrate over 2 copies of the group that I'm interested in. And up to analytic issues, so maybe I want to truncate this. I have a similar expansion. This is the so-called relative trace formula, where on the one hand, I have the periods that I'm interested in. So I'm summing over Cutts forms, which are distinguished as I'm as we're concerned with. And this main term is the so-called relatively, or the elliptic part of the RTF. And so here we're summing over certain double cosets where I have these now relative orbital integrals. So since this is the side that I'm going to be interested in for the remainder of the talk, I kind of just want to be a bit more precise about what these things are. So the terms that I'm interested in are so-called relatively elliptic orbits. So here the orbits are h of f cross h of f double cosets. So I have g of f, h of f, h of f. And I'm interested in relatively elliptic orbits, which are just those orbits for which this stabilizing subgroup, so gamma h1, h2 is equal to gamma, describes this group H gamma, is actually anisotropic mod center. So this is the relative analog of the elliptic locus that we saw earlier. And the terms are now these sort of relative orbital integrals over this sort of relative action. And the point here is that in this case, for a Zariski open subset of my group, these stabilizers are actually tori. So they're Rankine tori, and it's precisely these stabilizers which create the stability issues that we have to resolve. This stands in distinction from the Jacquet-Rawless relative trace formula, where the regular stabilizers were just trivial. So there was no sort of comparable issue in that case, which is why it was such a nice trace formula. Okay, so this is the tool we want to use. What's the actual putative comparison? So this comparison goes back to ideas of Jace Getz and Eric Wambach in a paper about 6 or 7 years ago, where they tried to develop a theory of relative twisted base change, and was recently also considered by Wei Zhang. So the idea here is we have on the bottom the trace formula that we were just describing, the 2-period integrals for Friedberg and Jacquet, and we want to compare this trace formula to a trace formula on the linear group. So the relevant functoriality should be the base change map. And the 2-period integrals that I'm putting on the larger group are going to be the linear periods, so relating to the results of Friedberg and Jacquet. And the second group here is another unitary group. So this is a different unitary group, sort of an inner form of my group G. And the reason for this comparison, the general framework of Getz and Wambach, is to view this unitary group as a symmetric subgroup of this sort of restriction of scalars, just a Galois involution. It's the fixed points of some Galois involution. And we can also realize these linear periods and unitary Friedberg-Jacquet periods as these subgroups as symmetric subgroups associated to a different involution. And so the framework, the point here is that these two involutions, theta and sigma, commute, and so I get a third involution just by composing them. And so this involution fixes this other group. And so that framework tells us, suggests what the comparison is. And importantly, in this context, we get a so-called a norm map, a way of actually matching orbits. And so this is the comparison we would like to prove. And it's interesting to think through sort of the spectral interpretation of what's going on here. But the sort of point that I want to kind of emphasize here is that this norm map only works over the algebraic closure. So here I have precisely the same issue as what was happening in the Arthur-Selberg trace formula. I could have two orbits which are in the so-called stable orbit, meaning that I can have H1 inverse gamma H2 is equal to gamma 1 prime, where now H1, H2 is in H cross H over the algebraic closure. And so I only get a matching of stable orbits. But nevertheless, this comparison seems to be the right thing to do. In fact, in 2018, Wei Zhang proved the fundamental lemma for the unit for this comparison. And in fact, there's a so-called arithmetic fundamental lemma in this context as well, related to the fact that in the work of Friedberg and Jacquet, there's a central L value non-vanishing statement. And so work of Chao Li and Wei Zhang also establishes the AFL for the unit in this case. So this seems to be the right comparison. And so we would like to make the relative trace formula associated to these periods stable, so that we can actually use this comparison to get results about these periods. So now I'm going to sort of talk about my work towards this stabilization. But before I do that, are there any questions? Okay. So the first thing to do is to sort of pre-stabilize things so that we can reduce to local harmonic analysis. And this is very analogous to what happened in the usual trace formula, although it's I don't think that, yeah, so the point is that we have a very similar structure, cohomological structure in this case. And so we can go ahead and sort of mimic the arguments of Kottwitz and actually the more sort of fully developed cohomological theory of Lebesgue to pre-stabilize the elliptic part of this trace formula. So here, again, this is my elliptic part of the relative trace formula. I'm summing over these relatively elliptic orbits. Whereas on the right, I now have a sum over these stable orbits, which are precisely the kinds of orbital integrals that are needed for this comparison that we saw on the last slide. And I, again, have to replace my relative orbital integrals with these relative kappa orbital integrals. And so once we have this result, we then reduce the stabilization of this relative trace formula to the study of these local relative orbital integrals. And so this is what I'm going to do now. We're going to go ahead and move to the local theory and study relative orbital integrals. So now I'll go ahead and assume that E and F are local fields. And most of what I'm saying for the next about few slides also works in the Archimedean case, but not much is lost if we just think about a p-adic place. So now I'm working over this local field. And instead of thinking about these relative orbital integrals, these double cosets, I'm also going to pass in the sort of standard fashion to just one copy of H. Remember, H of F is this product UW1 cross UW2. These orbital integrals on the symmetric space, which I'm going to call Q. So this is the quotient G mod H. So here Q is unitary mod UW1 cross UW2. And so now I have an action of just one copy of H on this symmetric group. And so I'm going to study these orbital integrals. So the way to do this is, recall I mentioned previously that this subgroup H is a symmetric subgroup. So it's the fixed point of some involution, which means that I'll be able to, I have this so-called symmetrization map. So I can take elements in gamma and I can map them to the gamma minus theta, and now reduce to just studying things on the symmetric space. So I want to do this because this is somehow the way that I'll be thinking about things when I want to define the so-called endoscopic spaces in order to study these kappa orbital integrals. So it's sort of very useful to think on the level of the symmetric space. And so now when I do this, the kappa orbital integrals that we saw on the previous slide just become these sort of orbital integrals or kappa orbital integrals on this symmetric space. So here I just wanted to write the formula for sort of what these kappa orbital integrals look like again. So I have these orbital integrals here, where now I've got my pushed forwards function. So S prime of F, say X, is the integral over, say gamma H dH. This is just sort of pushing forward along this, this quotient. And so I have orbital integrals on the symmetric space, and I'm twisting by this character kappa. Are there any questions with this? Okay, so these are the objects that we wanted to study, and now we're sort of in a situation analogous to what happened in the absolute setting. So I need to now introduce the appropriate analog of the endoscopic group that we should be comparing these kappa orbital integrals to. So for that, what I'm going to do is I'm going to follow, there's a couple different ways to do this. And I want to go through a construction which is more generalizable and relies and also recalls sort of the way in which you could have discovered endoscopic groups sort of yourself. So with that in mind, we just sort of recall the construction. So here I have, again, a pair, so X and a kappa, similar to in the absolute case. And I'm going to go ahead and assume that X is relatively elliptic, which, recall, just means that this stabilizing torus is anisotropic. And so the point here is I can understand kappa as a character of this cohomology group. And so Tate-Nakayama duality allows me to identify this cohomology group, sort of the first Tate cohomology group of the co-character lattice of this torus, which, since it's an elliptic, I get is equal to just this quotient of the lattice by some augmentation ideal. And so I can pull back to the lattice itself. And so through this sort of string of morphisms, I obtain a character of this lattice itself. And so this is sort of where endoscopic groups kind of come from. So in the adjoint setting, what did Langlands observe? Like in the adjoint case, these centralizing tori are maximal tori. And as a result, if I look inside this co-character lattice of H over the algebraic closure, say, I have the co-roots of my group. And so what we can do, I have a character on this lattice. Oh, no. So what did I have? I had the co-roots contained in the lattice. So what I can do is I can take the intersection of these co-roots with the kernel of my character kappa tilde. And the point is that this gives me a subroot system, and that subroot system corresponds precisely to the endoscopic group. And the reason that we deal with endoscopic groups as inclusions on the dual side is because we're dealing with these co-root lattices. So we would like to do something analogous to that in this relative case. But the first problem here is that this is not a maximal torus, right? This is h of lambda, or h of x is rank n, where n was the dimension of my Hermitian spaces, but my group is rank 2n. And so there's no natural co-root, there's no obvious one sitting there. But the point is that we can actually, I claim that there actually is a co-root system living inside this lattice. And the way to see this is to consider the so-called dual group of the symmetric space. So this is sort of a special example of a much bigger picture. We have, due to Gates-Gordon, Nadler, and Saklarudis and Venkatesh, to any nice enough spherical variety, including our symmetric space, we have a dual group. In this case, the dual group is going to be sp2n, and it's naturally equipped with a morphism. And so in this construction, if I were to have a maximal torus of my group G, I have the dual torus in its dual group, and I have the so-called canonical torus associated to the symmetric space sitting as a maximal torus of the dual group of the symmetric space. But this is not the group that we're interested in. We're interested in the dual group of my centralizer. And so the point here is I can view this morphism, this phi, as really just giving me a base point for a so-called dual symmetric space. So here I have, this is just the symmetric space of alternating forms, but I can realize it as this quotient because I have this base point. And the torus that I'm interested in is actually the quotient of the dual, of the maximal torus of this dual group by the canonical torus of the variety. So I have precisely the torus I want is equipped with a map to this dual symmetric space. And the point here is that this construction in terms of spherical varieties is, I guess, called a flat through this base point. And so the point here is that when we sort of turn this crank, this actually implies that the root system associated to this dual symmetric space lies in the lattice that we're interested in. So we do get a nice co-root or root system in this lattice. And so now we can go ahead and copy what Langlands did. We can intersect that root system with the kernel of my character kappa, and that gives us the following diagram. So this co-root system corresponds to what's called a descent of my symmetric space, which I can realize is just an orbit of an endoscopic group for G acting on this symmetric space. And so I get this top row here sort of fleshed out due to that root system. And the point here is that this top row is dual to certain symmetric spaces for elliptic endoscopic groups for G. It's kind of interesting. We see precisely like half of them show up. We need the ranks to both be even, and that's precisely what occurs when we go through this construction. And so this gives us a way of defining what we would think as our endoscopic symmetric spaces. So in order to make this a little bit more concrete and to write down what these symmetric spaces are, I'm going to go ahead and restrict to the unramified case, which is relevant, I guess, for the fundamental lemma. And so now I'm assuming that E over F is an unramified quadratic extension. And I'll go ahead and assume that both of my Hermitian spaces are just a fixed one, so a split Hermitian space of dimension n, which I'll call Vn. And what I mean by split is that I have a self-dual lattice contained in this symmetric space, or sorry, this Hermitian space. And this choice gives me a good notion of hyperspecial subgroup. And in particular, I get a good notion of like the integral points of my symmetric space in this case. Okay, so in this case, what are my unramified endoscopic spaces? What that previous construction gives us is the following. So for any decomposition of n, a plus b, I decompose my Hermitian space into a direct sum of split Hermitian spaces. And now I have this sort of unramified version of the symmetric space that I'm interested in, but I can think of this for any dimension n. So in particular, I can think of it for a and b. And so I'll consider the symmetric space associated to VA and VB of this form. This is a symmetric space of this. This is a unramified endoscopic group for my group G, so UVN plus VN. And so I define this to be my endoscopic symmetric space. So at this point, all I've really done is given a definition. It's not immediately clear that this is the right thing to consider. In order to make that, to state that this is the right thing to do in order to understand these kappa orbital integrals, I need to have a matching of orbits, a transfer factor, and so on. And so there's a couple of different ways of doing this, and I'm going to go ahead and explain it in a way which is, I think, most practical, even though it may appear kind of ad hoc. But the point is that we do have a nice matching of orbits and a nice notion of a transfer factor in this case. And really, the trick in this case is to observe the following diagram. So here I have my symmetric space, and remember this is being acted upon by two copies. These are the Unitary Friedberg-Jacquet subgroups. There's two copies of this unitary group acting, and so the point is I can quotient out by the action of one of them, and I can do the same thing on the endoscopic side. And it's a relatively straightforward check that when you do that, the categorical quotients can be identified as this vector space of Hermitian matrices, or Hermitian, matrices on the vector space Vn. So this is, why is this useful? The point is that this is the same thing as the Lie algebra of Vn. And this Lie algebra here is the Lie algebra of an endoscopic group, Va times UVB. And so once I quotient out here, I'm actually in the context of standard endoscopy for these Hermitian Lie algebras. And so while that doesn't necessarily solve the full problem here, what it does allow me to do is, you need to check that these quotient maps are well behaved on the regular locus, but they are. And so what we can do is we can use this map to give a notion of matching of orbits, and we can even get a good notion of a transfer factor. So here I'll just say that, an element, an orbit of an element here and an element here match if when I look at their images in these Hermitian vector spaces, they match in the sense of classical endoscopy. So this gives rise to a nice matching of orbits. And it also gives us a good transfer factor. On this space, I have the so-called Langlands-Shelstad transfer factor already well defined. And so the point is that you can show that just pulling back along this map gives rise to a good transfer factor comparing orbital integrals here. So to sort of make that clear, I'll say that using this construction, so this is maybe not the definition, you could think of this as sort of a result, but it's also works fine for the purposes of this talk. You can use this to show that for many test functions on this symmetric space, you can prove the existence of a test function on this endoscopic symmetric space so that we have the appropriate matching of orbital integrals. So there's some sort of like support constraints needed here because I'm pushing forward along this quotienting map, and so it depends on the sort of behavior of the sort of the singular locus of this map. But in any case, my hope is that this slide sort of shows you that those endoscopic symmetric spaces we saw on the previous slide are the right thing to consider. And so now that we have this transfer factor, I'll go ahead and state the main result, which is the fundamental lemma. So this is very analogous to what we saw the result proved by Ngo, Waltz-Bourget, and Hales in the classical setting. So for any regular semi-simple element of X in any character, there exists a decomposition and a unique stable orbit in this endoscopic symmetric space so that we have this matching of orbital integrals. So this is sort of the main result, and there's a typo here. But the point is that, so there are a few, this almost gives us the full stabilization of the elliptic part. At least it's true if we imply some support conditions. On some test function. But importantly, what we're missing and the sort of next big step is to prove the fundamental lemma for a Hecke algebra, not just for the units, but this is sort of understood to be the kind of like core result that's needed. So I have about 17 minutes left. I just wanted to, and I want to spend the rest of the time kind of talking about some of the components that go into this proof. But before I do that, are there any questions at this point? So the upshot here is that we essentially are able to stabilize this relative trace formula, or at least the elliptic part. So for the proof of this, what we're going to do is we're going to try and emulate, at least at the beginning, the proof of the fundamental lemma in the standard context And what I mean by that is we're going to reduce to the Lie algebra. So because we're dealing with kappa orbital integrals in this case, here this identity is between a kappa orbital integral and a stable orbital integral. We need to be careful about what we're doing. We want to descend, and so we just need to do this in a very precise way. And so the first thing we need to show is that these symmetric spaces have a good notion of what's called a topological Jordan decomposition. So just to remind people what a topological Jordan decomposition looks like, I have a product decomposition of certain elements, which are called so-called strongly compact. And what this is morally is if I were to take an element that was actually integral, so in the integral points of my group, and I were to look at its image over the residue field, then this decomposition reduces to just the standard Jordan decomposition on this finite group. And so it's sort of like a p-adic analog thereof. And these notations, this is called the topologically unipotent part. And this is called the absolutely semi-simple part. And the reason that we are interested in considering such a decomposition is that it allows us to descend to smaller symmetric spaces and ultimately to the Lie algebra in a precise way that allows us to keep track of the orbital integrals that we're interested in. Just a more delicate notion of descent. And so we have to prove that, okay, so if my element, so I have my inclusion of my symmetric space into the group. And so if the thing to prove is that if X has the topological Jordan decomposition as an element of G, then the individual constituents are actually elements of the symmetric space. So this allows us to sort of pull back the notion of Jordan, topological Jordan decompositions to symmetric spaces. And so this is not hard to check, and it holds for a general sort of p-adic symmetric space. And what this allows us to do is prove that the orbital integrals, the kappa orbital integrals that show up in the statement of the fundamental lemma, can be descended to kappa orbital integrals where now I'm only evaluating at this topologically unipotent part, and here my symmetric space is replaced by the so-called descendant of Q at this absolutely semi-simple part. So to prove this, we need to prove a relative analog of a result of Kazhdan's, a relative Kazhdan lemma. And these sorts of results hold for a quite general set of symmetric spaces. And so this, the ability for us to descend to the Lie algebra is pretty uniform across symmetric spaces. So this readily generalizes to other cases. And the reason that this is useful is that these topologically unipotent guys lie in the image of certain exponential maps. So we can pull back the statements to the Lie algebra. And so once we do all this and we take the transfer factors into account, we reduce the statement of the fundamental lemma to something I call the Lie algebra. So what are we really looking at? It's the tangent space at the unique fixed points under my group's action. So this gives me some rational representation of the group H, and it can be easily checked to just be isomorphic to the ring of matrices of my vector space. And the action is actually quite straightforward. It's just, if I take a matrix, it's just, and two unitary matrices, it's just the simplest, the nicest sort of rational representation you could hope for. And so once we've done that, we reduce to the statement on the Lie algebra, which is very analogous. So now I have a sort of, my lattice lambda gives me a compact open subset of this of integral matrices in this matrix ring. And so I'm going to take indicator functions there. And so this is the statement of the fundamental lemma on the Lie algebra, where again, we similarly match orbits, and we're comparing kappa orbital integrals to the stable orbital integrals. And I haven't defined the transfer factors here, but the point is that everything, it's quite analogous to that picture we saw on the symmetric space. Namely, I can quotient out by one unitary group, and I get a reduction map from my space of matrices to just the space of Hermitian matrices. And in this case, everything is very, very concrete. I mean, I'm taking a matrix here, and I'm just sending it to say X conjugate transpose or something. So it's a very concrete map. And what this allows us to do is to send to, again, the case where we're dealing with endoscopy for these unitary Lie algebras. Now, with that, you might be asking yourself, is all of this sort of just a elaborate reduction to some statement which was already known in the context of the Hermitian Lie algebras? I mean, we already have smooth transfer of the fundamental lemma, so perhaps we just already know these results. And unfortunately, that's not quite right. The problem here is that this reduction map is only well behaved when the matrix here is invertible. And so these integrals have a lot of singularities which need to be dealt with. And so if we want to push things forward, we have to be very careful, and it ends up requiring proving a lot of sort of new results. And so the point here is that when we look at this statement, I am ultimately just looking at orbital integrals at regular semisimple orbits. And so the observation is, though, even though this integral has singularities as x tends towards the degenerate locus, the actual orbits themselves are contained in this set of invertible matrices. So here I can identify this symmetric space of non-degenerate Hermitian matrices on this vector space as an open subset sitting here. And the point is that if we want to study the orbital integrals of this push forward, then it's useful to think of not in terms of this unitary Lie algebra, but rather this symmetric space. So the problem here is that this push forward is going to give me something non-compactly supported, but the crucial reason for reducing, in this case, to the Lie algebra is that this this test function has a lot of symmetries that were not available on the symmetric space itself. So a priori, all we know is that we have invariance with respect to the maximal compact of my unitary group, which is not very big, all things considered, but because of the extra symmetries afforded to us, we actually have some additional invariance for the maximal compact of the linear group. And so this implies that the way to study these orbital integrals is to study orbital integrals of functions on this symmetric space, which are invariant with respect to the maximal compacts of the linear group. So in order to do, I mean, because of this non-compactly supportedness, the way to do this is that we decompose this symmetric space into these sort of closed subsets, just sort of filtering by the determinant. And so now each of these sort of restrictions give me a nice compactly supported test function. And so the problem now reduces to studying these invariant functions on this symmetric space of Hermitian forms. How much time do I have left? Okay. And so in order to do this, so this sort of becomes the primary problem. And the solution is to sort of develop a theory of endoscopy for these smaller symmetric spaces. This was something I didn't quite realize going into things, but we needed to sort of resolve this problem of endoscopy for these simpler symmetric spaces, which are kind of easier in this case. So what I end up doing is I produce, so now I'm thinking about orbital integrals of functions that look like this. but not just those. In fact, they're things that are pushed forward from invertible matrices here. And so I can think about test function, the Hecke algebra of the spherical Hecke algebra for this linear group. And so in this context, it turns out that there's a nice morphism of spherical Hecke algebras. This is just sort of a twisted version of parabolic descent, which is dual to, say, the induction pi a twisted by a character, pi b twisted by a character. There's some parabolic descent. And so I have a diagram that looks like this. And the thing that ends up being true is that this, so again,
Leslie, I cannot hear you.
Hello, am I back?
And now you are back, but not your screen.
Okay, 1 second. Sorry about that. Don't know what just happened. Okay, sorry about that. So the upshot is that I proved that this sort of diagram, this correspondence of test functions, gives rise to sort of new explicit smooth transfers in the context of unitary Lie algebras. So in particular, what I would say is that for any spherical function on this linear group, I can either push it forward or I can apply this parabolic descent and then push forward to the endoscopic symmetric space. And that precisely gives me a matching of orbital integrals on this unitary Lie algebra. And importantly, this diagram proves the previous result. So in the last few minutes, I kind of just want to sort of give a quick reason as to why this proves the previous theorem, because it sort of touches on some really beautiful work of Hironaka. And then I'll make a few comments about sort of the spectral interpretation of this fundamental lemma itself. So why does this suffice to prove what we want? So remember, we were looking at the orbital integrals of, so I'm just taking the ring of integral matrices, but then I was restricting to the set of matrices whose determinant was equal to D. But that's just the same thing as looking at the push forward of the set of invertible matrices whose determinant is valuation D D over 2. So I can think about this sort of explicit function, which I'll just for shorthand call 1 over D over 2, as an explicit function sitting in this Hecke algebra. And so what I need to do is I need to compute what this is. And in particular, I want to identify it with something that would match precisely what I would be getting coming from the endoscopic side. So something that looks like this, or something like that. And so what we do is we use some sort of beautiful work of Hironaka's. She studied these invariant functions on the symmetric space and showed that there was an isomorphism of modules with respect to this Hecke algebra with a different Hecke algebra, namely the Hecke algebra of GLN over the ground field, F. And there's a commutative diagram where this is the base change map. So this is Hironaka's so-called spherical Fourier transform. And we have a similar diagram over here. A base change map. And so to prove that this fundamental lemma is exactly what we need in order to get the fundamental lemma on the unitary Friedberg-Jacquet case, we're going to use this diagram and move the problem over to one of these Hecke algebras. And the computation here is quite enjoyable. It requires some very explicit working with some Hall-Littlewood polynomials and some sort of enjoyable combinatorics in order to get that this works out. But once we do this, once we apply Hironaka's work and we study these, we conclude that this fundamental lemma here, this identity of orbital integrals here, suffices to prove the previous theorem. And so maybe I'll just end with a few comments about this reduction. So this identity that I'm proving is actually can be identified as a fundamental lemma for the full Hecke algebra for stabilizing a different relative trace formula. This is sort of one that's maybe a little less interesting from a global perspective because we already understand this, but it would be the trace formula of unitary periods. Where now I'm thinking of just my double cosets here are trying to indicate the two periods that are showing up in the trace formula. So it's not, so this relative trace formula is again, not stable. And what we're checking here is that the right endoscopic symmetric spaces just correspond to these smaller rank unitary groups, unitary groups. And so the point here is that in this case, we have that the role of the elliptic endoscopic group that we're rising in our case is being played by this Levy subgroup. And so that the spectral sort of analog for the fact that these are precisely the orbital integrals that need to be stabilized can be found in the work of Fagen-Lotin, and more recent work of Raphael Bozar-Plessis, pointing out that these local unitary periods, they satisfy a multiplicity less than one statement, except for induced representations. And so for these induced representations, there are more local periods. And what we're kind of seeing a shadow of here is that the spectral interpretation of these instability problems is related to these higher multiplicities. And so I just wanted to make that point because that sort of gives a hint as to what the spectral applications of this stabilization are going to be. And I guess I'll just, the actual proof of this final fundamental lemma is in and of itself quite involved and ultimately reduces to a global comparison of relative trace formulas. So sorry for the technical glitch in the middle, but I'll go ahead and stop here.
Thank you very much. Questions, please.
Are there, can I ask a question?
Of course.
Yeah.
Are there, I mean, this is an example of the Shimura varieties. And of course, I mean, this is a very good example to work out. But there are many other cases. Are there a chance of extending your ideas to these other cases that not all of them need a stabilization, but I suppose.
Yeah, so thanks for that question. So one natural family of examples, which I'm currently working out, are the so-called the Galois pairs. So if I take E over F, these sorts of pairs, which generalize precisely this unitary periods case. This gives us a large family of relative trace formulas, which are similarly have stability issues in lots of cases. So that's certainly a large family, and the this is one that I've been focusing on.
G is any reductive group? By any restriction on G?
No restriction on G. And that, yeah, the results, the descent techniques. In fact, when I was referring to the descent techniques about topological Jordan decompositions, is this case that I had in mind allows this sort of techniques. But I guess the boundary of these sorts of techniques is I'm looking at symmetric spaces for which the generic stabilizers are abelian, and so going beyond that sort of requires some inductive kind of consideration. Have I answered your question?
Yes. Yeah. I mean, that's a general example. But of course, I mean, I presume, I mean, I'm not an expert in relative trace formula, and I'm sure there are other examples that we probably can look at. But I mean,
yeah. So one interesting case, which was recently studied via the theta correspondence by a student of WITEC GAN, is SO5 U2. And that's another case that's I'm interested in because it's not a symmetric space, and so my hope is that by stabilizing these trace formulas, we'll be able to get some precise results on when you have period integrals which are not Eulerian, and that's precisely what WITEC student finds here, is that you get non-Eulerian period integrals.
Yeah. Thank you.
Okay. Further questions, please? Right, if there are no further questions, thank you again. So, next week we will have a lecture by Freidun Shahidi on multiplicativity of gamma factors and Fourier transforms via Braverman-Kazhdan program. You can see the abstract on the seminar calendar. So,
thank you all for coming.
Our pleasure.